Hi, this is Boat Anchor Audio. My name is Marty Dwyer. I have something here that those of you who work with operational amplifiers may find of interest. Now, it's no secret that operational amplifiers can be operated by a 2-wire supply or a 3-wire supply. I don't want to get into any religious wars here, but it seems to be the general consensus that it's easier to design a circuit with a 3-wire supply. Now, if you have just a 2-wire supply, traditionally what you do is use a rail splitter to give you the 3-wire supply. Nothing new there. But I was curious as to how this particular circuit would react to unbalanced loads, some loads which are seriously unbalanced. In other words, if one rail is drawing, say, 50% more current than the other rail, how would that affect the balance of the output voltage? Well, we did a number of tests, and at the end of this video I have a spreadsheet here that will show you the results of these tests, and I was surprised at how well balanced these voltages were, even with some loads that were pretty unbalanced. Anyway, let's get started by taking a look at the block diagram. We'll work our way through the block diagram, through the schematic diagram. We have a picture of the rail splitter, and we also have a picture of the results that we got from a number of voltage tests we conducted with this rail splitter. So let's get started by taking a look at the block diagram. Okay, here we have a very simple block diagram of the rail splitter. We have the mains going into a 2-wire power supply, have positive, negative coming out of the power supply. That feeds the rail splitter. Out of the rail splitter comes a positive, negative, and a ground. Some considerations that we want to look into is what would be the maximum load current this can handle. How well does it handle unbalanced loads? How well does it handle capacitive loads? What's the voltage regulation? And also we want to take a look at some circuit protection here. Make sure we don't blow something up. Okay, here's a schematic diagram. I'll tell you right up front, this is not all my work. Most of the work has been done by others. I don't know who did it, or if I knew, I would give them credit. But apparently it's been a community effort over the years. Various people have added improvements to the original circuit, and I've added a few minor improvements on my own. Anyway, take a look here at F1 and F2. Both of them are slow blow fuses. You're going to need slow blow fuses because you see in the diagram there's a lot of capacitance in there. If you put in a regular fast blow fuse, you're going to be tempted to overfuse it in order to keep the fuses from blowing. So we use slow blow fuses there. You also notice D5 and D6 are nothing more than reverse polarity protection diodes. If you're pulling an all-nighter, you've run out of coffee, you're a little tired, you hook up the polarity backwards, you're not going to blow it up. Okay, on the right-hand side, we see SH1 and SH2. What are they? They're nothing more than precision 1-ohm resistors being used as current shunts. This way you'll be able to put a voltmeter across it, measure the voltage, and thereby measure the current. You don't have to break the circuit and stick an amp meter in there to measure the current. You just use your voltmeter, measure the voltage across the shunts. Not shown here, but we also added a couple of heat sinks to keep things cool. Now here's the finished product. If you look at it, you can see in the upper left-hand corner, we got 2 terminals for a positive, negative coming in. And at the lower left-hand corner, we have 4 terminal block. Positive, negative, and 2 of the terminals are for ground. If you look in the upper left-hand corner, right by the 2 terminals, you have the 2 polarity protection diodes. Also, between the 2 terminals, you see 2 rectangular blocks. Now, they are the slow blow fuses. They've been soldered in. I may change that later. I don't particularly care for that anyway. It's something for the future to improve upon. On the far right-hand side, you see 2 resistors. They are the shunts. As I say, they're nothing more than precision 1-ohm resistors. Also, you note the 2 heat sinks. They are the TO220 type heat sinks for the regulators. Anyway, that's it in a nutshell. We're going to take a run over to the test bench and see how this works with the unbalanced loads. I'm kind of curious to see what happens when we load up one rail but don't necessarily load up the other rail, and whether or not these voltages will be balanced as they should be. So give me a second, we'll run over to the bench there. Okay, we're on the bench now. We're taking some preliminary voltage checks here. Now we're going to test this with a 12 volt nominal output. Now we've got 11.9 volts on one rail and 11.99 volts on the other rail. So it's pretty well balanced there. I'm trying to balance it a little bit better, but it's pretty good. I don't think too many op amps are going to complain about that. All right, now let's take a look at the current draw here. Now this is the positive rail current draw. We're drawing 132 mils on the positive rail, and we're drawing 78 mils on the negative rail. So this is pretty well unbalanced. All right, in order to get that voltage output, we have to put in almost 26 volts in. And again, we get 11.98 on positive and a minus 12.06 on the negative. So it's pretty well balanced. Now let's take a look and see how we can get this to work at plus or minus 5 volts output. And we're adjusting the power supply down to 5 volts. We're on the positive rail, and we have it pretty close to 5 volts. The load is still the same. So we've got 5.04 on the positive rail, and we have a negative 5.05 on the negative rail. Now that's pretty good. Let's take a look at the current draws. The positive rail is pulling 56 mils. The negative rail is pulling 32 mils. Again, it's pretty well unbalanced. 55 on the positive rail. All right, now what kind of voltage do we have to put in to get this? We need 11.7 volts input to the rail splitter in order to get our plus or minus. Okay, we've checked the rail splitter with two loads. We've checked both the positive rail and the negative rail, and to see what would happen to the voltages with an unbalanced load. Now that's just with two loads, in other words, two resistors. Now here we have what I consider to be a fairly comprehensive test sheet using various loads for both 5 volt and 12 volt. And you can take a look at the test sheet here, and it gives you an idea of what your output voltages will be under balanced loads and also under some pretty extreme unbalanced loads. So take a look at that. I'll leave a link down below. You can download it if you like. Okay, we're back again. I think we've seen what happens when you put unbalanced loads on this one particular rail splitter. The results, I think, are fairly encouraging. Even some loads that are severely unbalanced does not necessarily reflect to the output voltages. The output voltages are a little unbalanced, but not enough to seriously degrade the operation of an analog circuit. For some digital circuits that are especially finicky, you might have a problem, but even there, I think you're not going to have a problem with digital circuits with this rail splitter. We have loaded it up with some capacitance. We've put about 0.1 microfarad capacitance on it. The rail splitter is stable. It doesn't oscillate. It doesn't take off. It seems to work just fine. The voltages stay the same. So this can handle a little bit of capacitance. You're probably not going to find that much capacitance presented to this rail splitter in the average op-amp circuit. All the filtering is done before the rail splitter. I hope you enjoyed this. Our next video is going to be about how to use a tunable audio bandpass filter to reduce the total harmonic distortion that comes out of your audio generator. Now this will enable you to reduce the THD possibly down to as low as 0.03%, which I think is good enough for doing some serious audio testing. So until then, keep those electrons flowing. So long.